Okay, welcome back. Last time we talked about vector spaces, and now we're going to talk about linear subspaces. So linear subspaces consist of, or are made of non-empty, rather I should say, a non-empty subset T of a vector space S. It's called a linear subspace. Of S if it's true that for every A and B in S's field and X and Y in T, that AX plus BY is also in T. So should note that this implies that we have to have 0, the vector, in T. If you're not sure about that, think about it for a second and convince yourself. If you're still not sure, ask on Piazza, but that's the case. So, based on this, it's easy to show that T is also by itself a linear vector space. T is also a let's go through a few examples and we can consider whether or not they look like they would be vector spaces or vector subspaces. So the first one, if we're in R2, as defined previously, so we have the field of reals, and the vectors are made of pairs of real numbers. So let's go with, I'm going to plot some different examples. And normally at this point I would talk to the class, ask people to shout out or raise their hands or discuss whether or not things are indeed vector spaces. So we want a linear subspace. X2, X1. There's one possible subspace. Now let's go back to blue. There's another one. Pretend like that's a circle and it's centered on the origin. Actually, we don't even have to pretend. Let me see if I can do this. Oh, that's beautiful. Okay. So now we have this circle. We still have to pretend it's centered on the origin. Unless. Ha ha ha. There we go. So in this case, T is there. There's another case. Assume we had this, and finally this case. So, which of these are indeed subspaces? Well, starting with the upper left here, we can rule this one out immediately because it doesn't have the origin. So we need to have the zero vector in the vector space. And we can rule this one out on a variety of grounds. One is that we don't have the zero vector. Also, the fact that I could choose any vector here, multiply it by some scalar, and I would get something outside of the vector space. This one, the third one along the top row, does have the origin, so we do have the zero vector in there. But because it's bounded in its extent, once again, if we picked some value here, multiplied it by a scalar, say 3, we would get something out here that's outside. So that's not a vector space. What about this next one? This is a little bit trickier, isn't it? So here we have the origin included. It would be more obvious if I did draw this more straight. And if I pick, say, this point and I multiply it by 2 or any number, it's still in there. Okay, so that's, what about if I pick a point somewhere along here and multiply it by 2? That's still there too. Okay, so this is closed under scalar multiplication, but what about under vector addition? Well, under vector addition, if I had, let's see, could I get outside of this space? Certainly. We want this to be closed under ax plus by. Well, if I chose this point down here, shown in gray, which is in our space, and I multiplied it by -1, it goes up here, which is outside the space. So it looked promising for a moment, but it didn't make it either. Finally, this last point. Well, we have the zero vector in there. Any point along here that we pick, when we multiply it by a scalar, it just stretches it along the same line, up or back, and so that works. If we add 2 vectors on that line, we'll get something else on the line. So, in fact, this is a subspace. So, this one works. In the course notes, there are a bunch of examples for you to consider that we didn't put here because they're less easy to draw in R2. But take a look at those and exercise kind of the reasoning with those and make sure you got a good understanding. So that's it for this short lecture on linear subspaces. Next we'll talk about linear combinations and spans, which kind of grows out of this same topic.